Okay. All right. All right. 2 hours actually. 2 hours. Yeah. All right. All right. Thank you. All right. So it's 11 o'clock. So let's get started. All right. So if you haven't noticed, I updated your mastering with some practice problems. Right? Homework problems, practice problems, whatever you want to call it. All right. I suggest you get some practice. If you have an issue, and that's what I'm here for. Okay. But we're moving right along to chapter 2. And chapter 2 talks about Newton's laws of motion. Right? First chapter, we talked about patterns of motion and equilibrium. Well, in chapter 2, we're going to get more specific about the motion, right? We're going to start discussing the laws that govern motion, okay? So, and maybe I should put this on presentation mode. There we go. All right. So, the lecture will proceed as follows. First thing we're going to talk about is first law of motion, right? Then second law, and then we're going to talk about forces, right? Forces and interactions, okay? So force is what causes a motion, okay? For any object to gain motion, it must experience a force. That's a law. That's Newton's second law. So we're gonna go through all three of them. Okay? And lastly we'll end with third law and then we'll summarize. Okay? So the law of inertia, right? This is one that we are all familiar with. The law of inertia. Okay? The law of inertia says that whatever is in motion continues in motion until acted upon by an outside force. Right?
Can I get my pen?
Oh, is this your pen? Okay. Yeah, he handed it to me. So inertia is the force which keeps an object in motion that's already in motion, or it's the force that keeps an object at rest that's already at rest. It's either or, right? It's the same force. The same force that keeps an object in motion is the same force that keeps an object at rest when it's at rest. Okay? That's called inertia. Okay? I've said that maybe 3, 4, 5 times now. So if somebody keeps repeating something over and over and over and over again, that's a good indication that that's important. All right? So as always, we're going to skip the questions and we'll come back on another day and go over the questions when we have more time. Right? So here's an example of inertia, right? You pull the paper towel from under the coin, right? And the coin just drops straight down into the cup. That's the same thing. If you got a bunch of kitchenware on the kitchen table and you take the tablecloth and you can yank it away, and the things on the table will stay on the table and that tablecloth will come away. That's called inertia. All right. And we have some other examples, but that one is pretty straightforward. So let's stick to that one. Okay. So inertia in action, right? Rapid deceleration is sensed by the driver who lurches forward, right? So when we're in our car and we're driving and we want to stop suddenly, then what happens? When we stop suddenly, what happens to our body? We move forward. We keep moving. Yes. Your body will keep moving at the speed of the car. Right? However fast the car is going, when the car stops, if you don't have a seatbelt on, you will move at the speed of the car through the windshield. Right? That's called inertia. The first law. Okay? There's also an example of the second law, because no force the driver will. Because no force stops the driver while the brakes stop it. Okay, whatever. Alright, so we'll get to the second law. But here we're talking about it's the inertia which keeps the driver going forward through the windshield. Right? Same with you. That's why you must wear your seatbelt. Okay? So if I'm sitting on top of sitting in a plane, right? Remember we talk about the plane all the time, right? I'm sitting in a plane. I'm in the reference frame of the plane. So that means I'm moving at the same speed of the plane, even though I'm sitting still. I am moving at the same speed of the plane. But when I throw a coin up in the air, right, it goes up and it drops back down. If you're on a plane, you can test it yourself, right? You throw a coin up in the air and it's going to go up and come back down. It's because everything is with respect to the speed of the plane, because you're sitting inside of the plane. So the coin is moving at the speed of the plane as well. Everything is moving at the speed of the plane. Okay? That's the reference frame. And so, so if you, like I said, if you flip the coin up in the air, it seems like you're sitting here on Earth doing it. There's no difference. That's because everything in that plane is moving at the same speed. All right, I think that's a question. Newton's second law, right? Everybody in here is probably familiar, especially if you had a physics class in high school. You're familiar with Newton's second law. That's F equals ma, right? Force equals mass times acceleration, right? So the acceleration produced by a net force on an object is directly proportional to the net force. Did I read that right? The acceleration produced by a net force on an object is directly proportional to the net force. What? Is in the same. Oh, if they asking a question, I'm about to say, well, that don't make sense what they just said. But all right, the law of acceleration, right? So I must push. So for something to move, I must put a force on it. Okay. For something to accelerate, right? That's why the equation is F equals m times a. A is the acceleration. M is the mass. Okay? So from simple mathematics, right? If something is more massive, then what does that mean? In order for me to move it, I must apply more force. All right? That's F equals m times a. That's Newton's second law. and we can look at the cartoons here. Force of hand accelerates the brick, right? Twice as much force, two hands, right, produces twice as much acceleration. That's because we got the same mass. We didn't change the mass here, right? Y'all following what I'm saying here? We didn't change the mass. We only added more force. So it accelerated faster, right? Now, if we made this smaller, then what would that mean? And we didn't change the force, would it accelerate faster? Yes. If we made it bigger, it would not, right? And that's the case right here, right? We added another brick, and we kept the same force, and what? Twice the force on twice the mass gives the same acceleration, right? So the acceleration didn't change. Okay? So that's the equation, right? That's the equation. That's Newton's second law. I'm sure everybody in here has seen that equation in the past. Did everybody sign the roll? For those of you who just walked in, you should be paying attention to your mastering. You have an assignment on mastering now. Yes? Okay. And everybody should be enrolled. Yes, indeed. Well, we had a Mardi Gras this weekend? What happened? Seemed pretty scarce here. All right. So this is the equation for Newton's second law. All right. Force equals mass times acceleration. All right. All right. So Newton's second law of motion. Okay. So when we're in free fall, remember that's one of the situations we talked about in the first chapter. Free fall, a particular type of motion, free fall, right? We know that when an object is undergoing free fall motion, it's being affected by gravity, right? You know that when the only force acting on a falling object is gravity, with negligible air resistance, the object is in free fall, right? And an object in free fall accelerates towards the Earth at 10 meters per second per second. So that means every second, if I drop something from a height, after 1 second, if I drop something with a height, when I dropped it, how fast was it going? 0. When I first drop it, 0. When I first let it go, it's going 0. Not 10, but I know what you're saying, right? 0. But after 1 second, it's going to be going what? 10 meters per second. After 2 seconds, it's going to be going what? 20 meters per second. After 3 seconds, 30 meters. That is a acceleration. That is a change in velocity with respect to time. Okay? So what does it mean? It means that what? It means that two masses, right? This object has mass what? What's the mass of this object? M. Right? Has mass M. Right? See that? Half the force on half the mass. This object has mass what? 2M. So that means it's what? Twice as big. That's what that means. Mathematically, that's what that means. Algebraically, that's what that means. Okay? So we got to start learning how to think like that. If I say the mass is M, and I say, well, the other object has twice the mass of M, then the other object has mass what? 2 times m. Okay? But what we notice is that what? We still going to have the same what? G. So this means that what? It doesn't matter how massive the object is. It could be a bowling ball or a ping pong ball. They both will accelerate towards the earth at G. Right? So if I have a gun in one hand and I have a bullet in another hand, in my right hand, I got a gun in my left hand, I shoot the gun and drop the bullet. Which one hits the ground first? They hit at the same time because they will accelerate towards the earth at the same rate, which is G. Okay? Most people will say, oh, well, you know, the one you drop is going to hit the ground first because you shot that one. Well, that doesn't matter, okay? But we're not going to get into that. Just trust me on that, right? That I have a bowling ball in this hand and I have a ping pong ball in this hand. I drop them at the same time, they will hit the ground at the same time, okay? So, and the reason why this is true, right? Because here we go right here, right? We got a boulder and a feather, right? Now, some of you say, oh, well, come on. If I drop a feather and a boulder, they're not going to hit the ground at the same time, right? The reason why the feather doesn't hit the ground at the same time is because of what? Huh? I can't hear you. Materials what? Well, yeah, that's a reason why, but tell me the scientific reason why. Air resistance. Weight. Well, not weight. Not weight. No, sorry. But air resistance. So the feather does this because what? The air resistance is pushing back up on it. So it's falling like this, right? But if we were inside of a vacuum and we dropped that feather would drop just like a boulder in space. So imagine if you take the feather in space, right? Well, no, I take that back because in space, gravity doesn't affect anything. Everything's weightless in space, right? But I'm saying inside of a vacuum, space is a vacuum, right? Or a vacuum here on Earth is like, I'm trying to think of something that's a vacuum here on Earth that y'all familiar with. Outside of like a vacuum, you vacuum your floor with. I can't think of nothing right now. But anyway, let's get back to this, right? So this is very familiar. This equation right here is very familiar to the equation you learned in 3rd grade. And what is this? Circumference. Right? So it doesn't matter how big the circle is. It don't matter how big it is. The ratio of the circumference to the diameter will always be equal to what? Pi. That's mathematically true. Doesn't matter how big the circle is, how small it is, doesn't matter. It will always be equal to 3.14. Okay? That's what makes our math make sense. Is it true? I don't know. You shouldn't waste your time trying to figure that out. That's for the mathematicians. All right? But we've been using this, right, since the 3rd grade. Okay? And pi is just a ratio of a circle's circumference to its diameter. And it doesn't matter how big or small the circle is. It will always equal pi. Same difference here. Doesn't matter how big the object is, the ratio of the force to the mass will always equal gravity. Okay? So that's what it's showing you right here, right? This is a vacuum. This is like a vacuum tube. So you can imagine there's no air inside of here. So we can have a pump or something like that, a mechanical pump. We attach a mechanical pump down here and we can suck all the air out of here, out of this tube. And then if we drop those two objects in that tube with no air in it, this is what they'll do. They will fall at the same rate because there's no air resistance in this case. All right? All right. So, another question, right? Well, I'm gonna say the question. I'll say that for next time. Okay. So when acceleration is less than g, right? Non-free fall. Right. Non-free fall occurs when two objects acting on a force. Non-free fall occurs when two forces acting on a falling object. Right. So here we see the cartoon. Right. So we have. This force is due to what? Gravity. Your weight is due to gravity. So gravity pulls you down, right? And then your parachute is opposing gravity. That's why you don't fall to the earth like a rock if you got a parachute on. But if you didn't have a parachute on, you would fall to the earth like a rock. Okay? So, in this case, right, which person hits the ground first? Right, the heavier, right? So in this case, we have, it depends, the rate at which you go down is going to depend on your weight. In this case, right, but not in free fall. Free fall, everything falls at the same rate. But in this case, they had a parachute on, so that means what? The heavier person will hit the ground first. All right. Acceleration is less than the. We just talked about that essentially. These are questions, so we don't have a lot of questions on. So, forces and interactions. So now we're into forces and interactions, right? Because remember what we said about a force. A force is what causes things to move. Anything that experiences motion, it has to have experienced a force in order to be moving. Otherwise, it would be sitting still. Okay? So a force is simply a push or a pull. It's just an interaction between two objects, right? So the third law is every force has equal and opposite force. That's what the third law says. So first law is what? Inertia. Good. I'm glad. That's how fast that got to come off your head. Inertia. And the second law is F equal M times A. And the third law is every force has equal and opposite force. Right? And all of these things are life hacks. Right? They can be applied to life. Right? That's why physics is the study of the world and everything in it. All right? So we're all familiar with the law of action and reaction. We are familiar with that, right? If I slap you in your face, what you gonna do? Slap me back. It's that easy. It's the law of action and reaction. That's a universal law. So just keep that in mind whenever you're out there punching on people and talking about people, doing whatever you do. It's the law of action and reaction. Some people call it karma. All right? But in physical terms, let's look at it like this. All right? All right? So if I'm pushing on this wall right here, I'm pushing on this wall, right? The wall doesn't move, right? When I pushed on the wall, did the wall move? So did I apply a force to the wall? Well, why didn't it move? Because it applied a force back to me. It applied a force back. So the same force that I applied to the wall applied to me back. So in that case, we said it was what? The forces are in what? E word? Equilibrium. They equal each other. They just in opposite directions. That's a net force. Okay? So that's a law of, that's the third law, right? Action and reaction. All right? And yeah, co-pairs of a single interaction, neither force exists without the other, equal in strength and opposite in the direction. Okay, we just went over all that. All right. So here's just some cartoons that can help you understand action and reaction forces, right? You burning rubber in your car, right? Rockets, that's how rockets get propelled to break the Earth's atmosphere, right? The rocket puts a force on the Earth, and the Earth puts a force back up on the rocket and pushes it up until it reaches a distance where gravity can no longer bring it back down. Okay? We got a man pulling on a spring, right? And of course, when you pull on the spring, you know what happens. You pull on the spring, that spring is going to store some energy in it. And as soon as you let that, well, depending on how stiff the spring is, right? You might not be able to control it, okay? But let's say something you can control. You pull the spring, let's say the ping pong, not the ping pong. What's the thing? Pinball, right? You pull the little thing back, right, to hit the ball in the pinball machine. I don't know, y'all might not know about pinball, but it's a spring now, and you pull the spring, and the spring is storing energy inside of it. When you pull it, that's why when you pull it, you're gonna feel it tugging on you, right, to go back to its original position. That's the energy that you stored inside of it. It's pulling you back to its original position. That's a opposite, equal and opposite force. All right? And Earth pulls a ball. Earth pulls on ball. Ball pulls on Earth. Right? That's pretty simple. All right? All right, and like I said, we're going to go through these clicker questions on next time. So, what is this? We'll do all that next time. All right, so I think that's it. So, any questions for me? We're wrapping up early today, folks. So again, I hope you're paying attention to mastering. I've put an assignment on mastering physics, and it's all up there. It's all up there. In order for me to post it, I got to put all that information in there. And so you're going to see another one coming pretty soon for chapter 2. Yeah, we're ramping up. We're ramping up. Yes, sir.
I'm in mastering, but I don't feel like an assignment tab. I tried to go back to my course and stuff. So really, I don't know if I'm clicking the wrong thing or Nothing's popping up.
It should be at my lab. Are you going from the canvas?
From Canvas, yeah. Look.
Oh yeah, she did say that.
It's this one, right?
Yep.
Nothing pop up. I try to go to the scores and stuff. E-text. There's like nothing there. I don't know what this is.
Course home. Go to course home.
I don't know if it's like not loading or like.
Hmm.
I try refreshing it. It don't. Nothing pops up.
Okay. Boy, these folks.
Quick question.
Uh-huh.
So with the homework, is it? Do we have multiple like times to retake the? Okay, because like some classes, whenever they give the homework, they give you multiple chances to try to get a higher score. Is that how your homework is, or is just as soon as you send it, that's it, and then you move to the next one?
Man, we could do that. That's fine.
I just want to say.
Yeah. We could do that. Mm-hmm.
Yeah, no, I try refreshing it. Try logging in, logging back out.
Yeah.
I hit it.
Yeah. I don't know, man. Like this is what. Let me just.
Can I see that?
Let me see. This is what you should see, though. Let me
Yeah,
show
he was just one of my friends just showed me. Yeah,
he got it?
Yeah, he got it.
Oh, his work.
Yeah, but
So you know what?
But
Go
the guy-
see that course support tool
is
at
it
the
on-
top. That link
Is it,
course
is it on the canvas? Or?
on the canvas. Yeah. Go back to modules. Once you say course support.
Okay,
Yeah.
We said the homework starting this week, or it started already?
I posted it already.
Okay, it's due tomorrow.
I think it's like Wednesday.
Okay. Do it send like notifications or like when
It
you post
should,
it?
but you gotta set it up.
Okay, that's what I'm making sure. of.
Yeah.
Cause I didn't get it when you put it in there.
Yeah.
Thank you.
All right. Yeah, that's what I would suggest. Contacting that course support, and if they can't, I doubt if they can't help you. They should be able to help.
This never. I used it before, and this never happened before.
Yeah, they having all kind of issues with it this semester. I
Oh
don't
yeah, I don't know
know.
what's going on. Because at first, it wasn't. The link wasn't like. I figured out why like people wasn't able to sign in because the link wasn't working. Like it wouldn't let people click to go sign in. You had to, like, everybody had to do it on their phone instead of the laptop. Like it's a laptop, it wasn't working. Like the link. So I had to.